not every strange signal in space becomes a discovery. Some are noise, some are mistakes, and some, after years of checking, become a new piece of the universe. Astronomy is not like picking up a rock in a lab. Most discoveries begin as light radio waves, gravity, or tiny changes in a detector. A telescope records something from far away, and scientists ask the first careful question: is it real? That sounds simple, but it is the heart of the story. A signal can be shaped by the instrument, by Earth's atmosphere, by cosmic dust, or by the way the data was processed. So astronomers compare observations. They use different telescopes, different wavelengths, different teams, and sometimes completely different methods. A credible discovery usually survives this pressure. It does not have to be fully understood at first, but it has to keep appearing when the obvious errors are removed. This is why astronomy can feel slow from the outside and astonishing from the inside. The universe rarely announces itself clearly. It whispers. A planet may reveal itself by a star dimming slightly. A black hole may reveal itself by the motion of nearby gas. A galaxy may reveal its age through ancient starlight, stretched by cosmic expansion. What matters is not one dramatic image, it is a chain of evidence. And uncertainty is not a weakness here. It is part of the discovery process. Scientists often describe what the evidence suggests before they claim what is known. The memorable lesson is this: a real astronomy discovery is not just a surprising observation. It is a surprising observation that keeps surviving doubt. That patience is why the final answer can change how we understand everything beyond Earth. And once a signal survives, the next question becomes even more powerful. What is it telling us about the universe? The universe may be humming with gravitational waves so long and slow that no ordinary detector could hear them. This is one of the most fascinating signals in modern astronomy. A possible background, ripple running through space itself. Not a sound in air, not a vibration you could feel. A gravitational wave is a stretch and squeeze in space. Time usually made when massive objects move in extreme ways. We have already detected short gravitational wave bursts from colliding black holes and neutron stars. But this possible background is different. It would be more like a deep cosmic bass note built from many enormous sources across the universe. To search for it, astronomers use pulsars. A pulsar is the collapsed core of a dead star spinning rapidly and sending beams of radiation into space. From Earth, some pulsars appear to blink with astonishing regularity, like natural clocks scattered through the galaxy. If very long, gravitational waves pass between Earth and those pulsars, the pulses can arrive a little early or a little late. The change is tiny, but if many pulsars show a related pattern across the sky, that becomes a clue. The evidence suggests that something like this pattern may be present. Scientists are cautious because the signal is faint and separating it from other effects takes time. But the leading explanation is exciting. It may come from pairs of supermassive black holes slowly orbiting each other after galaxies merge. Why does that matter? Because it would let us study black holes. Too large, too distant, and too slow for ordinary gravitational wave detectors. It is astronomy done with clocks, patience and gravity itself. The takeaway is simple. The universe is not only seen through light, sometimes it is measured through timing. And a tiny delay in a pulsar's beat may carry the memory of giant black holes moving across cosmic history. A faint gravitational wave background would not be the end of a mystery. It would be the beginning of a new kind of astronomy. Here is what scientists can say, carefully. Several teams studying pulsars have reported timing patterns that look consistent with very long gravitational waves. The signals are not a single sharp event. They are more like a shared disturbance spread across many pulsars and measured over long periods. That is the known part. Pulsar timing is showing a pattern worth taking seriously. The uncertain part is the source. The leading idea is a population of supermassive black hole pairs. These would form when galaxies merge, bringing their central black holes into the same cosmic neighborhood. Over immense spans of time, the black holes would orbit each other and send out slow gravitational ripples. But there are other details still being tested. How many black hole pairs contribute? How massive are they? Are there unexpected sources mixed in? Could some features come from the way pulsars behave or from noise we do not yet understand? This is why scientists do not treat the story as finished. A careful discovery grows stronger when more pulsars are timed. More years of data are added, and independent teams keep finding compatible results. If the black hole explanation holds, the payoff is enormous. We could learn how galaxies build themselves over cosmic time. We could study giant black holes not as isolated monsters, but as part of the long life cycle of galaxies. We might even learn where our models of cosmic structure are incomplete. The most beautiful part is that none of this requires a spaceship reaching those black holes. Their gravity may already be written into the ticking of stars in our own galaxy. The takeaway is cautious but extraordinary. When astronomy finds a new way to listen, the universe often has an older story waiting underneath.